Working with music, I always took life for granted. It was part of the show. Now I can see that light affects people just like music affects people. I light up the city, the parks, the houses, and the streets. Light is a mood changer, just like music. With light, you can make the unsafe safe, the unavailable available. Challenges motivate me. I need to feel challenged in order to grow. Changing career was a very brave step for me. I left my comfort zone. I tried something new. I'm proud of myself. People often think that more light is the best solution. It's really about finding the balance.
Hello and welcome to another episode of our series of clean energy webinars as part of Hvdc cooperation between the Energy Division and Hvdc Management Consulting. Today we're going to present to you and discuss how FACTS and Hvdc as technologies are acting as enablers for the clean energy transition. As some of you know, the integration of large mix of variable energy resources or variable renewable energy resources poses fundamental challenges to the grid itself, especially with quite an extensive cyber-physical system is emerging. Different challenges drive the need for advanced power system solutions like FACTS and Hvdc. However, those advancements, as much as these advancements make these technologies viable today, they come as challenges to the grid and its operation. Today, our featured speakers will present their views on some of those challenges when it comes to operation, investment, and governance of the energy market. My name is Mustafa Ibrahim, and I work as a group manager for Hvdc T&D Sweden. I'm leading a group that works with FACTS, Hvdc, and integration of renewables. During the past 16 years, I've been working in different roles between research and been helping TSOs, DSOs, and taking different roles in the energy and electricity market sectors, to the point that I start helping people working with integration of renewables as developers and contractors as well. Here I'm hovering to our standard disclaimer and rights. Please take a few seconds to skim through them. These will be in the slide pack list, so you can go through them afterwards. And here's a list of our featured speakers for today. We have 4 speakers from 4 countries. We have Magnus Olofsson visiting us from northern Sweden. Magnus, you may present yourself.
Yeah, I'm Magnus Olofsson. I have a background in the power business for many years. I've been managing R&D in various positions. For the moment, I'm within ISCAN, International Smart Grid Action Network, where I'm national expert for Sweden, and I'm also Nordic Senior Advisor for Downing, Renewables and Infrastructure, among all.
Mm-hmm. Thank you, Magnus. And I'm sorry I have to break the habit of introducing our speakers in a chronological manner, but we are going with the same order of the presenters. So Iris, you're second. Maybe you present yourself.
Thank you, Mustafa, and hello everyone. My name is Iris Baldursdóttir. I'm an electrical engineer. 20 years ago, I took my master thesis here in Stockholm in KTH, so it's nice to be back. And then I've been working for ABB in Sweden with FACTS technologies, but most of my time I spent with Landsnet, the TSO in Iceland, in various positions, the last one being Executive VP for System Operations and ICT, and always very involved in the intelligent power system. Right now, I'm the senior advisor at ENTSO-E in Brussels, working also on system operational challenges and strategies and linking them to the needed research, innovation, and developments.
Thank you, Iris, for being with us here today. And I'll move to our dear colleagues, Stephen Woodhouse from the UK. Maybe you present yourself.
Good morning, everybody. I'm Stephen Woodhouse. I'm a director with AFRY's Management Consulting Energy Division. I've been with the company for nearly 25 years. Prior to that, I worked with the UK regulator, and I had some time in the transport industry before that. So I'm a career economist, and really my work in the energy sector has always related to the organization and I would say the disruption of the energy markets. So I've worked absolutely across the value chain, a lot of work for interconnection and new technology projects, and right the way through to retail, aggregators and new entrants. And I've worked across the world, really. Most of my work has been in Europe. So we've been responsible for creating innovative market designs which value flexibility.
Thank you, Stephen, for being with us here, even if you couldn't make it. Last but not least, I would like to present our colleague who works in T&D in Sweden, but he's currently based in Chile. Maybe Gabriel, you should present yourself.
Thank you, Mustafa. Well, my name is Gabriel Orguin. I'm a power engineer by training. I could say my career has been a mix of distribution planning engineer, transmission planning engineer, and latest year as a consultant and adjunct professor at one of the local universities here in Chile. My expertise is basically HVDC and fax devices in the early stage of the project, especially conceptual engineering system studies.
Thank you, Gabriel. And now, before we start, through the session, please ask as many questions as you can. You can send your questions to energyconsulting@afry.com. I'll try to cover as many as possible of these questions during the presentation. However, we'll be able to reach out to the senders and respond to their questions. The slide packs and recording will be sent to all attendees and audience, and the ones who couldn't make it live will receive it as well. And now we can start with Magnus Olofsson's part. Please go ahead.
Thank you, Mustafa. I will give a brief summary of what I see happening in the power sector with relation to the topic here of HVDC and facts. And I would say one of the key challenges going forward is more or less what we see for the moment. I mean, when we have had kind of low wind production part of the year. And here is a study that is actually looking at that and the probability for having like several days, multiple weeks possibly with low wind and possibly low sun, solar power production also. So that is something to keep in mind when we design the power system for the future. Then we have some solutions, of course. We have hydrogen that can be used for storage, as well as hydropower or reservoirs, not to be forgotten. But not all countries do have that resource. And we have also long-distance transmission that can, for example, connect hydropower with remote areas with no hydropower, but can also balance out areas where you have kind of low wind with other areas where wind is blowing. And some people say it's always blowing somewhere, and it's actually true for sun also. It's always sun is shining somewhere and somewhere on the planet, but then you need to really have extensive networks, grids. And to make it simple, I think it's not hydrogen or grids. It would likely be both. But we should keep in mind that, for example, battery energy storage, that's very efficient, and super capacitors as well. I mean, you're really going to the short time frame. But if you're going to store seasonal, or at least for 2 weeks or something for low wind periods, you might think about hydrogen, but then you have to think about also losses that, as you see in this example from NREL in the US, that they claim it's around 35% efficiency. It's fairly low for going from power to gas and gas to power back again. for some industrial processes, you can actually use hydrogen, for example, for green steel and so on. Then you would reach a higher efficiency naturally, because you don't go the other way back to power. But here the focus, I would say, is more on the power system, on the transmission system, and then we have some kind of tools there. We have the HVDC, where we can go with cables, and of course overhead lines, but people tend to be resistant to too many overhead lines, at least in more populated areas, and then HVDC is good because we can have cables with no limitation of length for transmission. And we have also seen HVDC breakers coming up, so you can potentially have actually grids with connected DC lines, not only point to point, which is kind of an interesting development going forward. Between HVDC and HVAC, you would use converters, I mean, for example, in the point-to-point connections. And then if we stick to the HVAC case, we have a tremendous toolbox of FACTS solutions. I will come back to that later here. Cables. The benefit of cables is obvious, that we don't need to cut the trees, for example, here in Sweden, and to make the right of ways for overhead transmission lines. The drawback, if you do it on the ground, is that you get a lot of joints. You can't transport these bulky cables with a very long length because it's simply too big. The drums, they're going to be too big. On a ship, you can do it with a very much higher length and avoid a lot of joints. So that's a benefit, clearly. Just to be mentioned, quite obvious. But we have also seen, as I said, innovative DC breakers. This is from the Swedish company Cybrake. I actually worked for them for a while. Can say that also. And this is the breaker that they are developing. And ABB, they have a solution, and there are also other vendors having DC breakers. So this is an opportunity where you can actually connect DC grids, because if you go to the history, this was kind of a limitation, and is still a limitation, that you won't connect DC lines together because it's hard to interrupt the current. So you don't have any zero crossings. So you need to go to converters. But this is an opportunity going forward. And in particular, if you look at the sea-based grids with cables that are growing, like for example in the Nordic Sea, with energy islands and so on, it's kind of interesting to think about DC breakers as an opportunity for making meshed or connected DC grids. And here is just a picture from ABB on a converter station. I mean, nothing special, but it's a lot of talk about semiconductors and the lack of semiconductors. And in this we have big and many semiconductors, by the way. If we look at countries applying cables for wind, I can just list those four. I put Sweden more into bracket because it's to be seen. We have UK that is clearly on the route to put cables in the sea from north to south for transferring wind power in the north, and also in the sea, by the way, into the southern part of the UK. Germany, they do it on land because they don't have much sea there to use for that. Japan, they are planning for wind power from Hokkaido, from the northern island to the south, and by the way also solar power from the southern island up to the Tokyo area. And in Sweden we have the Sydväst link and the Southwest link that has been recently taken into operation. Not sure if we can really connect it to wind, but somehow maybe we can. But there are also discussions and ideas about how to connect north and south through the Baltic Sea, but that's more proposals. I was part of the organizing committee of last week webinar at Royal Swedish Academy of Engineering Sciences, and we had Zach Richardson, and I borrowed this slide from him, and I'm actually showing the next is the material slide with content, and it says about our plans for reinforce, and of course they are reinforcing on land quite a lot, but they are also looking at subsea options, which are naturally all HVDC. You see 3 lines going from the north to the south, and it's kind of funny that in all those examples, UK, Germany, Japan, and also Sweden, it's always from the north to the south when you talk about wind. So wind is naturally more in the north, and I mean in many cases, like in Sweden, it's more that it's less densely populated area, so it's more about permissions and so on. We can also just have a look at what the EU is doing on this area, and here is just an example on technical requirements for connection to HVDC grids in the North Sea. So here are some technical solutions on how to arrange those meshed, or maybe not meshed, they don't have to be meshed, but connected DC grids in the North Sea. And it's kind of likely that we will see a DC grid growing. It's actually started already in the North Sea, so it's kind of interesting. I saw that Norway, they are reorganizing Statnett with some reference to this also. Germany already mentioned, I think we know it. We have these HVDC corridors. It says planned, but this is an old slide. It's actually ongoing. And this is an idea actually from Japan. So I had to check that with a colleague within the ISCAN community, Dr. Yasushi, and I asked him, is this really true that you're going to put HVDC lines around the whole of Japan? But then he said that please reuse my slide, and this is an extract from his slide saying that you have planned HVDC submarine cable between Hokkaido and Tokyo. So that one is planned. It's more kind of close to be real, and then it's also considered a line, and that's for solar power to the southern island up to the Osaka area. So that's going north instead. If we look at Sweden and the Nordics, you can compare the graph or the chart from 99 to, I can't see it here now, it's 2020, yeah, correct. So this is more than 20 years, and you don't really find many new, or almost no new line in Sweden, at least no longer line. So we have a backlog, and meanwhile the grid has been aging, so we have older lines that need to be refurbished, and we need to meet the demand that is increasing heavily. And this is an idea from Per Norberg, who is a foreign professor at Chalmers and also from Vattenfall, and he proposed actually a sea cable for Sweden going from mid-Sweden down to the Stockholm area, as you see on the right part in the sea there, and also some 800 kV AC. I think I skipped that one. I can just say that if I go to facts, we are actually seeing a declining capacity in Sweden from north to south, and this is the southernmost bottleneck that is actually has been decreasing for several years. So how can that be? Have we taken away lines? Yeah, of course we take more out operation for maintenance and renewal, but it's also that we have lost nuclear in the south and we got wind in the north, so it's also stability problems. But then, just my final remark here, it's on facts. Then we have an enormous toolbox of facts technologies, and we should use these because these are built-in stations, so it's normally not a problem with permissions that you need to wait 10 or 12 years to get kind of a new lineup. This is, meanwhile, we should really use all this StatCom and other solutions as much as we need that can be taken into operation in a few years. Just one word also before I end, that's on digitalization. Of course, this has a risk of increasing vulnerability of the system. And this was actually a program now that is taken into operation between the Nordic funding agencies and the TSOs in the Nordics. And I was part of this when I worked for Nordic Energy Research recently. And this is a very important work to consider, and also reliability, of course, in the system. But it's more work to do here to get a more agile system. Okay, that's my part of it. Thank you.
Thank you, Magnus. Well, I can see that your slides have summed up lots of topics, touching a base on high voltage cables, submarine cables, fax business, and the need for these technologies. And it was interesting to see as well how the network looked like over 20-21 years.
Thank you.
Thanks a lot.
Thank you.
And now we're going to move to the next part, at which our presenter Iris will go through the prospects and the roadmap for the clean energy transition. And we are going to discuss a little bit about the ENTC's vision for this roadmap. Please go ahead.
That's right, Mustafa. Thank you very much. I'm going to actually start my presentation by just introducing ENTSO-E for those who maybe are not familiar with it. This is an organization, the European Organization for Network Transmission System Operators for Electricity in Europe. And it's the Association for the Cooperation of European TSOs. Our members are 42 TSOs representing 35 countries. And they're all responsible for the same task of a secure and coordinated operation of the European electricity system. And I always like to point out here that the European system is the largest interconnected electrical grid in the world. And we have an historical role of technical cooperation, but you can also say that ENTSO-E is sort of the voice of TSOs in Europe. And we have now a 10-year history of great cooperation between thousands of experts in the different TSOs. I will focus on the ENTSO-E Vision 2030 and our RD&I roadmap for also the coming 10 years. And I'll select some bits and pieces from there, looking at HVDC and FACTS technologies in particular. So the European electricity system is truly undergoing a significant change. It's driven by the strong climate action plan and more renewable energies. And of course, we're always seeing changes, right? But this change is really happening at an incredible speed, and it's opening up a lot of different challenges for system operators and for the electricity market. And these challenges come in many different layers. So ENTSO-E decided to bring their experts together and create a vision. This is the first vision of its kind, to look at both the system operational perspective and the market perspective. And seek forward-looking solutions to facilitate Europe's societal goals of a secure, affordable, and clean energy future. And you can hear already now that I am quoting some of the targets presented in the EU 2030 targets and the clean energy package. And it's truly supporting the EU targets. And its assumptions to the vision are built on the 10-year network development plan assumptions. And in particular, the distributed generation scenario, even though all of them are pointing in the same direction of the same fundamental trends. And we see that wind and solar energies are increasing. They're being connected to the distribution grid, so distributed energy sources. On the consumption side, we see new kinds of users, prosumers coming in, and smaller industries as well. Also, the cross-sector integration is going to happen and will need to happen in order to increase efficiency. And then we're talking about electricity, heat, gas, and transport sectors. Here we also see the digitalization, and I noticed that Magnus talked about the vulnerability of digitizing the grid. And we're really referring to a cyber-physical system where information and communication technologies are enhancing the physical grid utilization and providing the architecture and tools to manage the future grid. Another important aspect that I want to emphasize is the need to align markets and physics. we need the market to fully reflect the physical and the technical constraints of the grid going forward. With the increased renewable electricity, we also see the increase in power electronic interface generation. And here are the scenarios for 2030, showing the Nordics going up to 35%, but Ireland and continental Europe all the way up to 60%. The European system has been built as an AC system, but there's also a huge increase in HVDC technologies, and mainly due to the fact that we need to transmit more energy over longer distances, but this is also linked with the offshore energy production. And the offshore is one of many aspects that are necessary to consider when developing the future grid. And there is a lot of discussion going on now on offshore, and NSOE is taking part in that exchange and has been developing several position papers on the topic. The last one was published in July, focused on system operation and governance. So take a look at the webpage with all the information available. System stability challenges and how to adapt. And why is the system stability such a hot topic? System inertia is shown here to decrease looking forward from 2025 until 2040. And this means a less stable system. And I recognize this very well from operating the Icelandic grid, which is an islanded system with 100% renewable energies and very, very low inertia. And there we needed to take several steps for handling the stability issues that Landsnet was experiencing in the grid. And then I would like to refer to, for example, the Migrate project, where a pilot was implemented to implement a wide area control system, and through that improve the stability in this low inertia grid. So summing up the vision and the key drivers, I think we've been through all of them. It's distributed flexibilities. This is a very simple term for a very complex topic, and requires a close cooperation between TSOs and DSOs. The rise of power electronics and the path towards a hybrid AC/DC system, markets and physics integrated, offshore wind, energy system integration, and of course mastering the operational challenges. But what do we do with a vision? We can put it in the drawer and hope for the best, but we know that that's not likely to bring us anywhere. And that's why we also have a roadmap. And then I'm coming to the research, development and innovation roadmap of NSOE, which is built on the 10-year network development plan and also the vision now for the first time. And this is an important tool to steer us in the right direction and really focus our efforts on the innovation needed. What is different from previous roadmaps? Because this is the 6th one in the row. I would say that this roadmap is focused more talking about technology readiness level of different technologies. It's focused maybe with a bit more emphasis on demonstration and implementation part, because we really want to accelerate the transition, accelerate the uptake of new technologies. The roadmap presents 6 flagships in 3 clusters, and I use a big red pointer here to point at the cluster which is of relevance here to the looking at enabling the large-scale offshore wind energy, enabling the secure operation of a widespread hybrid AC/DC grid, and enhancing the control center operation and interoperability. And to take this even further, we have developed an implementation report which was for public consultation this summer for the coming 5 years, with concrete project concepts going forward, where we are defining with stakeholders what research is needed in the field. And I want to touch upon some of them. First of all, the interoperability concept. With more HVDC links, multiple converter systems from different vendors, there comes the need for improved interoperability. And we're referring to here a kind of a vicious cycle where to offer technological solutions, manufacturers need specifications. But for TSOs to write specifications, they need experience. And with no experience and no specifications, there's no offering. So this is the vicious cycle that we're referring to here. And in this report, we're talking about the demonstrations needed going forward and the target environments and the standardization of these technologies. Looking at the technical challenges for the system operators today, we see the stability topics here with frequency stability, voltage stability topics, and we see that there are several solutions available in the market, but they're not widely applied. Compared to the past, we need more flexibility to the grid and more controllability. And the good news is that the power electronic devices that are coming and being linked to the grid have a potential that is not fully used yet. And we see also that HVDC can deliver some of the required functionalities, but appropriate planning is needed. So for damping and flexibility, I want to name a few examples of how HVDC comes in as a solution. HVDC is able to provide synthetic inertia to compensate for the inertia lost in the system when we go to PEIG systems, both by drawing them between different asynchronous systems and also by installing, for example, a DC, a storage on the DC side. We can also provide ancillary services through HVDC links, and this has been done in several occasions. For example, the BritNed link between the Netherlands and the UK, where 100 megawatts of frequency containment reserve is provided to the UK through the cable. So there are several examples of this, and by moving from the single point-to-point connections to a multi-terminal system, there are more functionalities that are interesting for the grid. And we can ask ourselves, will the DC system be the backbone of the AC system in the future? Grid forming is an important topic, and we have defined 7 grid forming capabilities, and are also stating that HVDC with modular multi-level converters, FACTS devices, battery storage and PPMs are able to provide these solutions. And I will not go into any technical detail here of the grid forming solutions, but there's a white paper out there available. And finally, last point, but not the least, even if it doesn't involve the investment in large infrastructure, it's the need for modeling and tools to fully represent the characteristics of the future grid, both for planning and development purposes, but also for real-time operations. And then there's the challenge of the computational efficiency needed as well. To summarize what has been said, we know that the power grid is migrating from a traditional AC system to a merged AC-DC system, and the operational challenges are quite well studied, and we know what we want to focus on. But in order to cope with all of these challenges, we really need innovation, research and development, because the solutions are not fully ready, all of them to be commercialized and used in a big scale yet. And the cooperation with various stakeholders is also crucial. So with that said, I am finishing my presentation for now, and I want to thank you for listening.
Thank you, Iris. I'd like to remind our audience today that they are still able to ask questions during the whole webinar. They can ask the questions by sending it by email on energyconsulting@afri.com. And we have received a couple of questions already, and 2 questions towards Iris, and 1 sounds to be more towards Magnus. So we'll move ahead with the remaining parts, and I hope to answer as many of these questions. Next part, we're going to talk about the future energy system needs and challenges from electricity market perspective. Please join us, Stephen.
Thank you. And thank you to Magnus and Iris for setting out a few of the different dimensions of this. So I'm a generalist in some senses, and that's because I've been involved in the challenges to the energy system since I came into the business nearly 25 years ago, and I've looked at it from a lot of different angles. I'm very curious. I don't like doing the same thing for very long. I even spent a couple of years, I had an interlude as our former company Peru as chief digital officer, and one of the projects I worked on at that time was in fact the NSOE project about the white paper on the cyber physical grid. So Iris, you made me smile when you were talking about that. I had a conversation with a friend of mine at a TSO that said the grids themselves aren't secure. You chuck a bicycle over the fence and short out a transformer. So we never designed the grids to be secure in the first place. So cyber security is an issue, but there's lots of other security issues to be concerned with. So if we could start my slide deck, please. We're in a world that is changing fast, and the changes that we've seen over the last 20 years as we've brought renewables into the grid, I think we're in, the territory of you ain't seen nothing yet. So we're looking to completely decarbonize our economy, which, notwithstanding hydrogen, can only be done with a vast degree of electrification. But very helpfully, it's electrification of things like heating and transport that have storage inherently built into them. So we're seeing quite an expansion in total demand. If we're not careful, we will see quite an expansion in total peak demand, but that isn't necessary. So we see a very different pattern of generation in the future, which will drive totally new needs while removing supply of flexibility. And a lot of that flexibility will be at the lower voltage level. So we're moving away from a centralized world where we control large power stations to deliver the services that we need, to a world where those services are delivered at a micro scale by much smaller resources. So if we could move to the next slide, please. One of the critical technologies is offshore wind. So we are not in a world where generation is being decentralized and taken to a micro scale. If anything, the next wave of renewable technologies will be bigger than anything we've seen before, but it's the control that will be taken down to a micro scale. So we're actually seeing the big generation is separate from the control technologies and the flexibility providers. So again, coming back to the EU's work, so Magnus mentioned some of the technical coordination work. The EU set out, the Commission has set out some scenarios for how we reach 2050 goals of zero carbon, and offshore wind in their scenarios ranges from 230 to 450 gigawatts of capacity, which is just incredible. And we're already seeing the development of offshore networks, but there are some real challenges both in the regulatory and the business model, which we'll come to later. So of course, you don't develop offshore wind with AC. We're talking about very large scale DC technologies there. So when we step back and look at the transition of our power system to one that's led by renewables. So even the 2020, on the left-hand side, you see the patterns of generation over a year that make up, or actually, in fact, this is a month, that make up demand. This is an example for Britain, but you see it everywhere in Europe. As you see the degree of intermittency rising from 2020 to 2030 to 2060. And we've in fact been working on projects like this for more than 10 years. We did a groundbreaking study on intermittency in Britain and Ireland in 2010. And even the picture for 2020 looked very radical compared to what we'd seen before that. So if you look at that world and zoom in, you see that there are flexibility challenges, there are locational challenges, and there are investment challenges. So these are really what we see the drivers for change on the power system. So renewables are not in the same location as the traditional generation, either at the transmission level or at the distribution level. So we see a need for investment in grids, but more so for better congestion management techniques. Flexibility is a huge topic in its own right, but we're pushing conventional providers of flexibility out of merit and replacing them with technologies which ordinarily wouldn't be providers of flexibility. And I'll zoom in on that topic in a moment. And the last big challenge arising from the mass adoption of renewables is the investment challenge. It completely changes the business model and even the streams of value on which investments are taken. And that's true both of the grid investments and of the investments in the generation and some of the supporting technologies like batteries. So if we can move to the next slide, please, and just look at that first topic of location. So we are developing at a mass scale gigawatts and gigawatts of generation technologies in locations which haven't traditionally seen generation. So coming back to something that Idris mentioned, the 10-year network development plan, we're seeing over 46,000 kilometers of potential cable development and cables and lines, of which nearly 60% is DC. So the ingress of DC technologies to our grids is growing fast. And we've seen already that Britain is using DC offshore connections as an alternative to building onshore just because of the difficulties in getting planning permission. So, DC technologies are coming very fast into our system. We've just done a project looking at a system called NEOM in Saudi Arabia, which was intended to be a 100% renewable energy fueled system and ultimately to export hydrogen. But they're planning to create a new city with tourism and industry there. And one of the topics we looked at was whether we could actually use DC as the backbone of the core grid. We weren't able to see the value driver that would make that an attractive proposition, even from a technical perspective. You move the problem of frequency management to become a problem of voltage management, but you still have the same fundamental problem that what goes onto the grid and what comes off to the grid must match instantaneously. But obviously with DC, you get more control over the components. But it didn't look like the right solution to us at the time. I think there's still some technological developments needed before we could run a DC-oriented grid. But maybe that's part of the debate later on. So if we could go back to the slides, please. The next challenge is really the interesting one. And this is where we're doing next slide, please. This is where we're doing a lot of work on how to organize and design the markets for energy. So we see new challenges for all types of flexibility. So on this slide, I'm concentrating on things relating to active power and frequency management. But even within that, we're seeing a real diversity. So if you look at the rows, we see needs for real-time flexibility, and that can go right down to zero. It can be 0 millisecond response, by which I mean inertia. There are synthetic inertia products that are really, within milliseconds, right the way out to the standard primary, secondary, and tertiary response. So there's kind of real-time, I would say, post-fault frequency management. The next tier is intraday. So this is dealing with the fluctuations of wind and of solar energy during the course of the day. So ideally that would be dealt with within the energy markets themselves as we get fine granularity of the settlement interval and close to real-time trading. The next flexibility challenge is meeting peak capacity. So that's the old capacity in a traditional thermal system. And the final one is the seasonal challenge. And in the Nordic area, that's an old challenge, having enough energy during, the period when your energy comes into the system, the rainfall period, to meet your demands for winter energy in an electric heating world. So ordinarily there's enough energy in the system, but is there enough seasonal storage? And that's going to be a challenge in the world where we use solar energy in the summer and electrical energy for heating in the winter. So that's a new challenge in some areas and perhaps not a new challenge in others. But when we look at all of these different timeframes for flexibility, you could meet all of those with a gas-fired power plant, with a traditional fossil fuel plant. Once we move away from those technologies towards renewables-led technologies, we start to see some different challenges. So if we look towards the right-hand side, we look at the technologies that you might use to meet all of those different timeframes. Interconnection is one of them, enhanced transmission. And I don't just mean building more grids, I mean more intelligent use of the grids. So one of the topics we've been working on for a number of years is the way in which interconnector capacity can be used not just for the bulk transfer of energy at the day ahead stage, but for the transfer of flexibility and system services. So as I say, we will see the need to create value streams and markets for all of these different timeframes for flexibility, and it will involve quite a lot of new technologies. So if we move to the next slide, please. Investment is the real challenge. We need to find ways of meeting the investment needs of the new providers, not just of the grids, but of the supporting technologies. So we have to assess the socioeconomic benefits, but we have to have mind for the business models, the regulatory feasibility, as well as the technical feasibility. And I won't dwell on this, but I'll just give an example. One of the first projects I worked on when I joined the company in I joined in 99. It was a year or two later, but it was the North Sea Interconnector project between Norway and Britain. And that fell apart in the end because one of the consequences of an interconnector from Norway to Britain would be to raise Norwegian prices, and it wasn't politically acceptable. And more recently, we did a study that looked at the degree of coordination between the Nordic TSOs. And we concluded that on the investment, really investment in the Nordic countries is done for national interest, not for Nordic interests. So if we move to the next slide, please. We have been working on these topics for many, many years. We work on analysis of the socioeconomic benefits of various types of projects, including interconnection, and we can do the same for some of the technologies that deliver system stability. We've done a lot of work with clients on the business models. The regulatory feasibility is a topic in its own right. We did a project a while ago looking at the concept of hybrid offshore assets. So this is HVDC assets, which are both a wind farm connection as well as an interconnection. And that gets extremely interesting when you're looking at topics like who underwrites the risk? Is this an asset which is primarily a connection or an interconnection? How do you deal with the capacity allocation, and so on. So that's a very rich area where some real interesting market design has to take place. And the technical feasibility, well, we do work on those topics as well with our colleagues. We're involved in some of the Horizon 2020 projects, looking at how you make these things fit together. So I'd like to end on that note. We are able to help with all of the aspects of the feasibility, both the commercial, the technical, socioeconomic, and regulatory for any of these innovative projects. And I'd very much like to hear from you if you've got interesting projects of your own. Thank you.
Thank you, Stephen. It's been quite informative, I got to say. The thing I could say that the three of speakers have been touching base on flexibility issues. A lot of talks about offshore grid integration, and I've got as well a question about this. But before coming to the question part, I'd rather move to the last part of our webinar, which is a case study from AFRY on Kimmel-Lugere, and correct me if I'm pronouncing it wrong, as always. It's a case study at which an HVDC project is under development to resolve the energy challenges in Chile. Please go ahead, Gabriel.
Thank you, Mustafa. Let's go to the next slide, please. No, the previous one. This is the agenda. Okay, this is the agenda. I'm gonna talk a little bit about Chile's variable energy resources. I'll touch on the associated challenges to Chile's electricity carbon neutrality goal by 2050. I will use the loadability curve of AC line to illustrate the value of fax devices and HVDC controllers to increase loadability of transmission corridors. And finally, I will briefly introduce the Kimal-Aguirre project, also known as the decarbonization line. Before moving to the next slide, please note that the north of Chile has one of the highest solar irradiations in the world. And this, of course, is driving the future development of Chile's power grid. Let's move to the next one. Chile has established ambitious clean energy goals, such as the electricity carbon neutrality by 2050. But today, the energy matrix is still rather dominated by dispatchable fossil fuels power plant. The figure on the left shows September 9th and 10th dispatch of generation technologies. Fossil fuels and hydropower are today the dominating generation technology. But as you see, solar and wind are increasing their share in the energy matrix. Coal-fired power plants and other fossil fuel generation technologies are located along the Chile's territory, most of them located in the north of the system. A decarbonization initiative has been promoted by the current administration. And what you see on the left, on the right of the figure, shows the decarbonization calendar, which aims at disconnecting or reconverting all coal-fired power plants by 2025. The challenges to be faced by the power system to accommodate the new variable energy sources require, as Stefan and other colleagues already said, reinforcement of the existing transmission grid, a new and robust north-south transmission corridor, and more controllability by fax devices, including energy storage. Let's go to the next slide, please. Chile's electricity regulatory framework includes a long-term energy planning, which is not mandatory, but a powerful guide for the expansion of the transmission grid. The long-term energy planning is a regulated process undertaken every 5 years by the Ministry of Energy. It considers 30 years of energy demand and generation forecast. The transmission expansion plan, on the other hand, is also a regulated process performed every year by the National Energy Commission, our regulatory body. And this transmission expansion plan considered the long-term energy planning performed by the Ministry of Energy and market player proposals. The latest long-term energy planning has recently been released and updates the latest assessment of the variable energy resource. The map shows the renewable energy potential for all regions of the country that were considered in the recent update of the long-term energy planning. The estimated renewable potential is more than 2,000 gigawatts. Main load centers are the metropolitan region in the center of the country and the northern region of Antofagasta, where Chile's mines are located. Let's go to the next slide, please. As already said by my colleagues, in the context of power system operation, the consensual response to clean energy challenges is grid flexibility. Grid flexibility is nothing else than the capability of the power system to maintain the continued balance between generation and load resulting in increased grid efficiency, resilience, and increasing integration of variable renewables in the grid. This special capability of the grid can be obtained by a mixture of market and technology solution. And in particular, as for the grid technology, grid flexibility can be enhanced by using grid energy storage, ancillary services, of course, expansion of the grid, and HVDC solutions, among others. Let's move to the next one, please. This is an old but always useful figure to explain the loadability of AC line and the value of controllability. The loadability of AC line is shown as a function of the length of the transmission corridor in per unit of the surge impedance load, or CIL, and somehow applicable to any high voltage level. The figure shows the three fundamental factors that limit the loadability of any AC transmission line: thermal limit in short line, voltage regulation limit in medium length transmission line, and finally, stability limit in long transmission line. The light blue line shows the loadability of AC line without any kind of compensation. The dashed line shows the loadability of AC line with fax devices or controllers. And finally, I have it green, but it seems green, okay. Shows the loadability of HVDC line. As you can see, controllability increases the loadability of AC lines, but HVDC is basically the strongest and most powerful controller of a power system. Let's move to the next one. And now I'm gonna introduce the Kima-Lo-Aguirre project. This is a regulated transmission project which will interconnect the solar-rich northern region with the load-intensive and hydro-rich center and south of Chile. The project is the result of the transmission generation optimization, and as I already said, it's key in the decarbonization process of Chile energy matrix. The HVDC project will run in parallel to the existing double-circuit 500 kV system, which is already congested during day hours due to the northern solar power production. The project will be bipolar 1500 overhead transmission line with dedicated metallic return, rated 3000 megawatt at plus minus 600 kV HVDC LCC technology, and is expected to enter commercial operation in 2029. Next slide, please. And just to close my presentation, AFRY has been supporting a developer of this HVDC project as its own engineer. We've been providing HVDC engineering support, system impact studies that verifies fulfilling the functional specifications and Chile's grid code requirement. We have also been supporting the developer with regulatory, strategic, and commercial advice. Of course, with the review of preliminary HVDC converter design by vendors. And I think I have already run out of time, so thank you for the presentation.
Thank you, Gabriel. And thanks to our audience for being with us. And we're running a bit short on time. However, we have received few questions. And I think the questions are actually touching a base on all speakers, some of these topics. Then we got a question about the hydrogen pricing versus the HVDC. We have gotten a question about Migrate project and how it improved the stability of Icelandic grid. We have questions about the minimum system studies, and we have questions about flexibility issues, but maybe I'll get a chance to pick one of them. There's a question about synthetic inertia and if it can substitute actual generation in the system. Do you believe in synthetic inertia? And the question is to you, Iris.
Yes, I believe and I've seen in studies and pilot projects that you can actually provide synthetic inertia to the grid and through that compensate for some, at least, of the inertia lost in merging to power electronics. So yes, there is certainly some solutions there to be found, and referring back to the Migrate project where Landsnet took part in setting up a world-first pilot, a practical approach to improving stability in a low inertia system by applying wide area controls based on facial measurement units, for example. So I've experienced that firsthand, and there we could actually improve the power flow, we could improve the congestions in the grid, and the security and the reliability of the operations overall.
Thank you, Iris. We till yesterday we have had more than 300 people registered for our webinar, and from 44 different countries, and we have received a couple of good questions. I hope that we will be able to answer them with your assistance, of course, to reach out to those audience. Just to sum up, the discussions went from discussing the TSO's remakes of the future grid. You and Magnus have discussed both issues about vulnerability, both on digital level and both on stability issues. And then later on, this topic about stability have been moving all the way in different aspects from network vulnerability to actual flexibility concerns. And the flexibility came both as a need and as an issue at the same time as Stephen presented. And later on, there were some discussions about the vicious cycle and interoperation between the TSOs and the manufacturers for those technologies and how they can cooperate in these. To just sum up, there were some few keywords. I would rather say flexibility is a need and a concern. Correct me if I'm mistaken here. And flexibility comes at different time frames, and according to what you discussed, Stephen, flexibility comes with different investment needs that comes at different times depending on the time frame for these. So I'm thankful to each of you for touching a base on some of these challenges, and I would like to remind our speakers that and our audience as well that they will receive the slide packs and the answers to their questions within the coming weeks. The slide packs and the recording will be available tomorrow. And please reach us on our emails as presented in this slide. You have each of the speakers' emails. You can reach them directly or can reach us on my direct email or energyconsulting@efri.com. And I'd like to remind our audience that there are actually 2 upcoming webinars. One is starting tomorrow at 10 o'clock BST. It's about grid digitalization. And the later one is coming on the 30th of September about hydrogen technologies. I thank our speakers today for joining us and the ones on distance as well. Thanks to our audience, and I wish you a lovely day. Thank you.
Thank you.